Well, so there are three major types of rocks in geology: igneous, sedimentary, and now metamorphic. We are to the third of three, and that signifies that we are moving on towards the latter portion of this course. And I know it's been a lot of stuff. Let's get through one more major section of rock types, and then we'll do some wrap up after this, and you'll have a geology course. So, what does this metamorphic word mean here? What's going on? So, things change. Rocks can change depending on the conditions. And the conditions that we're going to talk about here are pretty extreme. Right? So, yeah, as an example, consider these strata here. Let's say that these are some limestones and some sandstones, and maybe some shales, right? So, these nice sedimentary units are just kind of minding their own business, right? And you guys know what that is. That's one of those igneous intrusions that we talked about before. Make a big batholith and maybe a volcano. So, what's going to happen? What's going to happen to these nice, calm, sedimentary rocks when you get all this heat from an intruding magma coming into play? And also, as it happens, you can have some pressure, not so much from an intrusion, but from some of the other types of metamorphic agents that we're going to talk about. So the two main things we're going to talk about are heat and pressure. There are some other options. We're going to talk about some fluids and stuff like that, but mainly it's about heat and pressure. Well, think about our stability fields on our phase diagrams. You've seen a lot of phase diagrams in this course, and they're usually set up on heat or temperature. Those are actually different things, but we'll talk about them interchangeably for now. Heat or temperature and pressure, or depth in the earth you could use. Sometimes we'll add composition, but that's not as much involved in the metamorphic ones. Well, so what happens, we talk about, and I'll get a little more in depth in this in another slide, but we talk about movement on that phase diagram. And so what happens when you move from one field to another? And what we're going to do is we're going to recrystallize our minerals. Now, technically, we can have metamorphosis if we don't recrystallize to a different mineral. We could recrystallize a calcite in this limestone here, recrystallize it to a calcite again, just a new calcite, and make a marble out of it. And so it doesn't have to change which mineral it is, but the recrystallization, new crystals. That's the important part of what makes it a metamorphic rock, is something has changed and everything about the rock has recrystallized. All right, so over here we have a picture of a nice banded gneiss, and note the way I said that. Gneiss as in N-I-C-E, banded gneiss as in G-N-E-I-S-S, and we'll talk more about that when we get into the types of, or the classification of, metamorphic rocks. So what causes something to change into this right here? And remember, metamorphism is change. Well, heat is a major factor causing change. Pressure, you put it under, I mean, we're talking massive pressures here to change it. And then another way is that you introduce some really reactive fluids, and usually heat is involved with this. We're talking about hydrothermal alteration. You've got hot, maybe water-based fluids, sometimes other. But think about at Yellowstone, how you've seen the geysers. Well, that hot steam and water coming up through there, it's got all kinds of aggressive chemicals in it as well. And those things cause changes in the rock that they're moving through, that they're percolating through. And that can be an agent of metamorphism also. You do need some time for metamorphism to happen. If you just, well, now that I said that, I want to back up. There are some versions of metamorphism that can happen almost instantaneously with outrageous things like asteroid impacts and stuff like that. But for the most part, sometimes I see time listed as one of the agents of metamorphism. Not most of the time though. So usually you're going to see heat, pressure, and then sometimes fluid, and sometimes we're going to talk a little bit about shear stress and faulting. I want to point out this neat new site that I found. I'd never seen it before. Geology for Rock Climbers. So metamorphism can happen at a lot of different places and environments on the planet. So in a general sense, if you bury stuff more deeply, like under a convergent boundary, a continental collision, you get it buried deeply down here, so it's under a lot of pressure, and you know that there's a geothermal gradient, and so heat increases as you go down. So there we have two of our needed agents of change, and usually that's the two that we're going to talk most about is heat and pressure. And so you start getting minerals changing there. So metamorphism is happening. But you can also have metamorphism with just one or just one major type of agent. So we can get, so here we've got magma plume and so some magma coming to the surface. Well, like I showed in that earlier image where this magma is moving through, in this case, oceanic basaltic crusts, or moving through sediments over here in the volcanic area, you can get a change just from the massive heat involved. We'll call that contact metamorphism, where magmas or other very, very, very hot units are contacting rocks and causing them to change. You can have regional, where we were talking about like the burial. You can have dynamic, where, look, there's a lot of stuff going on as this whole lithospheric plate right here gets subducted under this whole lithospheric plate right here. This is a giant collision of things. So there's a lot of force, a lot of energy going on right here at this, where they're contacting each other and shearing across. We'll call that dynamic. I would point out that this is definitely not an either or, and we're going to talk about how these grade into each other. You can have regional metamorphism with contact metamorphism going on inside it, and then some dynamic on top of that. All these things can live together too. We're just going to talk about them in order to split things up and talk about different types. So that upwelling magma, applying the heat, you can get contact zone metamorphism there. Same idea as I showed in that earlier slide here. And you have that contact, where the magma is contacting the rock, is where the idea comes from. So putting together these slides causes me to go back and think about some of the terminology that we use, just throw around in geology without thinking about it. And one of these is regional metamorphism. Okay, I just talked about contact metamorphism, and that kind of makes sense with a magma contacting my other rocks. But then I switched to a different way of talking about it with regional metamorphism. And let me explain where this is coming from. So when we talked about plate tectonics, we talked about the formation of Pangaea, and see how you've got Africa here, and then a little bit of the European stuff slammed into North America, creating the Appalachian and the folded valley and ridge system. So this whole area or region is what gives us the idea of regional metamorphism. So in that area, you've got Pangaea being formed, and this is the African stuff riding up over the North American stuff here, and you get faulting and you get burial. Deep burial is a really important part of regional metamorphism. And so here you get this entire region. Here there's a map of the eastern part of the United States underlying this geologic map, and you get a whole region here that is metamorphosed together. You can follow it all the way up the Blue Ridge. And so that's where the idea of regional metamorphism comes from. Third type of metamorphism is idea of dynamic metamorphism. So this is due to shear forces. Now, shear forces means that there's a directionality to them. If you just bury stuff deep, deep, deep down, everything's under pressure, but it's pressure the same from all sides. As opposed to, here's a situation where we have some faulting going on, and so you have these big arrows on the faults mean that this side, this fault block here on the left, is going to move that direction upward, relative to this fault block, which is going to move downward over here. Later on, if we get to talk any about faulting, this would be called a reverse fault because of the direction. So they're pushing together, like something like Africa and North America slamming into each other is pushing from the right and from the left. These sediment packages or sedimentary rocks or whatever it is, pushing them together and causing them to shear along a fault and move. And in process, they're going to apply a lot of pressure. And so what's going to happen to this mineral crystal right here along the boundary between those shifting giant packages of rock? Well, what's going to happen to that guy is not going to make him happy. It's going to be some total recrystallization. His entire life is going to change because of the forces that are applied to him. Mention the temperature and pressure here. So these kinds of environments could be associated with high temperature, but not necessarily. So a lot of different things could be happening, and that's why this is a separate type of metamorphism, and we'll talk about diagramming where all these are in a little bit. And of course, we're going to get phase diagrams involved again, right? One of the things I wanted to do this slide, I'm gonna change the way they've got this arrow on here, and I'm going to talk about it going the other direction. So I'm going to mark that out and make it go in this direction for a reason I'll explain as I walk through here. So we got up instead of there. Okay, so so our phase diagrams, they represent a stability field. And I don't know how clear I've been about what's going on here. So this is a graphing idea, so that we represent things on a graph so that we can interpret what's going on. Okay, so what we've done is we've made an x-axis here with temperature. This time it's in C. And we've got a y-axis with, in this case, billions of pascals of pressure. Okay, so this just gives us a space, and I talk about it as a space, but that's in a mathematical sense, right? Because it has an x and a y dimension. I don't mean that it is a certain place on the planet. That's gonna come into play here, because we are going to talk about how we graph things given a certain place on the planet. But geologists tend to look at things on graphs if we can. I would point out I know we have one person that at least has a chemistry minor, and I wanted to point out this is a new thing you've probably not seen before in the chemical formulas with those superscripts in the square brackets, and those are coordination sites. Definitely not something you need to worry about, but if you're ever going to go on to inorganic chemistry, the coordination number of these different things means a lot. And you see they're like, these are both aluminums, and we talked about this a little bit early on when we were talking about how we could have the M1 and M2 sites. Well, it turns out that these guys they look very similar in a kyanite, but still aluminum and aluminum in a sillimanite. It's the exact same formula here, but something has changed, and so you have a forward coordination system for one of the aluminums. So it's acting differently within the crystal system. Even though the formula is exactly the same, these are different mineral phases. They're both solids, but they are different kinds of solids. So remember how the phase diagram works. If, let's say we have something at 0.3 gigapascals and 800 degrees C, right there. That red dot, if you have a mineral form right there, sillimanite is the stable form that's likely to form right there. But let's go to green. If we're over here, let's say that our mineral instead forms at 400 C and 0.8 gigapascals. So that is under much more pressure, but under less temperature. So in that green spot, if we had, let's say from an igneous melt, if we had this mineral form, it would form as the kyanite version instead of the silmonite version. All right, so that's the igneous idea, right? So, but if you have our little red mineral sitting nice and happy here, right? And suddenly the conditions that it's living under change to this green one, and you give it time, it will actually shift from this red mineralogy to this green mineralogy. And it'll actually reorganize its crystal lattice to do that. You can do that by changing the pressure. You can do that by changing the temperature. If you just have the green sitting nice and happy and you don't change the pressure, but you start heating it up because like more magma was coming in or something like that, you can go back into silmonite again. And there's even a third version called andalusite here that we could have under a specific low pressure and medium temperature range. So you're going to see that referred to with a stable phase on the temperature pressure diagrams, phase diagrams. So an idea we need to talk about here is different metamorphic grades. Not all metamorphism is created equal, apparently. So if you look up here in the top left of the diagram, we're very low pressure and we're very low temperature. So up here, we're just talking about normal sedimentary, let's say, conditions. So you do get lithification going on there, diagenesis. But we get more and more drastic conditions as we go down and to the right, down and or to the right on this diagram. So that's because of the increasing temperature going to the right, the increasing pressure going down. And if we go far enough, we'll eventually get to a zone where we're starting to melt. Igneous processes, so we're talking about melting the rock and going to a magma. I would mention that scale on this diagram, so this is in pressure in kilobars. So a kilobar is about 100 megapascals or 0.1 gigapascals. So even at the bottom here at 10 kilobars, we're talking about 1 gigapascal. And you've seen some of my diagrams before where we're talking about much, much more than 1 gigapascal. And so just to point out that all of this metamorphism that we're talking about, burying stuff deeply, is still within the very, very, very top part of the planet. So even all these different grades of metamorphism are just in the very, very, very surface part before we start melting or going to other igneous processes, our rock systems. Okay, so grades is one thing, but really since we could do it increasing temperature faster than we increase pressure, or we could do it by increasing pressure faster than we increase temperature, or we could do them both at about equal rates, we need to divide this diagram up more than just low, medium, and high grade metamorphism. So in comes this idea of metamorphic facies. And we did talk a little bit about sedimentary facies and how we had a sand depositional facies, a shale depositional facies, and a limestone facies. Well, same idea. We have metamorphic facies where we see groups of minerals and forms that tend to work together. They tend to be stable in the same parts of those phase diagrams. And so up here in the very low temperature and pressure zones, we get something called a zeolite facies. Zeolites have a very open structure. They're usually like phyllosilicates or sometimes tectosilicates, but they have a very open structure to them. And so that open structure seems to indicate that, well, They recrystallize, but not under a whole lot of pressure because they're not very dense and they're too open for that, right? So you could increase your pressure and temperature and get into what we call a green schist facies. That indicates a little more of both, as opposed to a blue schist, and hopefully I can show you some pictures of these. A blue schist facies, where the minerals indicate, well, yes, a lot of pressure, but not so much temperature. I mean, it's high-ish temperature, but not as high compared to the pressure that it's under. Or the other version, the hornfels, you can get much higher temperature than you're getting pressure. So you see how it's not, the temperature is increasing drastically, but the temperature is increasing drastically, but the pressure is increasing, but not near as drastically. And then you get an amphibolite facies, you get a granulite facies. And granulite gets a little touchy because this dotted line here, that dotted line is where things are starting to melt. So the granulite facies we're talking about intersecting with, well, is it still going to be a metamorphic rock, or are we just going to melt it and turn it into a magma at that point? And that is a valid question with some of these rocks. And then down here you get the eclogite facies, where it was just under such extreme pressures. We're getting to those other parts of the planet down close to the mantle where eclogites are happening. And I'm going to start in the middle of this diagram. So I'm going to talk about here in the middle that as the metamorphic grade increases from, on the left, non-metamorphic, to here, very low grade metamorphism, medium grade, to very high grade metamorphism. So you'll see that we have those clay minerals that we talked about with smectites and illites and muscovites and stuff like that. Well, I should say illites and not muscovites, because as we ease into the very lowest grades of metamorphism, we start to see those clay minerals reorganize. You don't have so much smectites anymore. You turn them into chlorites and maybe into muscovites. And muscovites, you remember, are those big platy versions. One good direction of basal cleavage. You pull them off in sheets. Well, those tend to form in your lowest grade of metamorphism. And then if you continue a little further, low to medium, we start to see the muscovites shift into a biotite phase. And then eventually they start turning into garnets. And you can actually turn your schist, and we'll talk about that as a rock type, into a garnet version, so that they weren't there. These garnet gem minerals were not there before. They start to form because of the grade of metamorphism that we're going to be under. Okay, so I started in the middle there, and I'm going to go up to the top and talk about rock types. So those clay minerals are typical of a shale that we talked about with sedimentary rocks. You start to metamorphose that low grade, we turn a shale into a slate. Even higher grade, we turn it into a phyllite. Eventually, a schist. And then at the extreme ends, we can turn it into a gneiss. Those are all rock types along the top, and they're typified by these mineral assemblages in the middle. And now to the bottom of this diagram, and it's interesting to note that quartz is just, yeah, we get quartz in sandstones and some in shales and stuff like that. It's stable under non-metamorphic sedimentary conditions, but you start metamorphosing it, and it's still stable as quartz, and medium is still stable as quartz, and high grades is still stable as quartz. So what happens is your quartz will recrystallize from the original quartz grains into new quartz mineral, and then it'll recrystallize some more, but also still into quartz. And so these recrystallization events are a little harder to pick out with the quartz minerals, where the mineral stability diagram extends across the whole thing. And here we have an example of that last slide kind of in action. So you can see that we're burying this deeper and deeper as the colors grade downward. So when it's buried shallowly, you're going to turn these minerals are all aluminosilicate minerals. so that we can talk about what happens to a given mineral chemistry under these different circumstances. So at the shallowest burial, so we've got some pressure from these overlying mountains, some but not a lot, and we've got some temperature because of geothermal gradient, so we're like 200-ish C. So that greenish color there represents a chlorite. Chlorite? I don't know why I added the extra syllable. A chlorite mineral assemblage. And you see how it fits low on the scales here of grade. If you bury it even deeper, that same chemistry would tend to shift over towards biotite, assuming, of course, that it's got the iron available. These are mostly iron-containing phyllosilicates and nesosilicates. So, but that's a little deeper, higher pressure, and it's also going to be a little higher temperature, right? Biotite zone. We skipped the muscovite. There's the biotite. I guess that's because we had the iron available. And then we're going to get down to eventually where I was talking about it can start to become a garnet under much higher temperatures and much higher pressures. So you get a higher grade. And then below that, we're starting to talk about shifting it. And here the chemistry has shifted a little bit without the irons in it to the Andalusite and the silmanites. But you see how you're increasing it and you're changing sometimes just the mineralogy, sometimes the mineralogy and the chemistry as we're going down to deeper and deeper or higher and higher grades of metamorphism. And one other big deal that we're going to need to talk about with metamorphic rocks in general is this idea of foliation. So foliation is a texture that can develop in metamorphic rocks. What's happening is you get a lot of stress in one direction. So you get, this one is showing it pushed from top and bottom. Often it's from the sides if you get a lot of regional faulting going on, like we talked about with Africa slamming into North America. So you get, what happens is these originally randomly oriented minerals end up oriented all so that their flat sides are all lying perpendicular to stress. Now, I want to be careful here and not make you think that all that's going on is that it's reshuffling these. Remember that we're talking about recrystallization. So it may be that this mineral right here is not exactly this mineral right here. It may be that the individual silica tetrahedra and the individual, let's say these are biotites, and the individual iron cations, all the individual pieces that make up this mineral might really be sort of dissolving. It's not exactly dissolving because we're talking about solid state diffusion, but it's sort of like it's dissolving and reforming. And when it reforms, it's no longer just random. It's going to reform so that its long axis here is perpendicular to the stress. So that, remember, is about recrystallization. What's covered up here, I didn't realize I'd covered it up with the image, is that this requires that the directions not be equivalent. If you just bury this without having one direction of stress be more than the other directions of stress, then the minerals won't orient like this. So foliation helps us to determine what's going on with metamorphic rocks, but it's not always there. You can have metamorphic rocks that are non-foliated. So sometimes we get to use foliation. Here's an example. The reason I grabbed this image, this is from the British Columbia text. It shows a nice one. So you can see where this piece of rock used to be a shale, and you had those, they're sitting diagonally. Now, those are the original bedding planes, like the sedimentary rock had bedding planes. That was what those were. But this rock apparently got buried and subjected to differential stress. And the stress was, they have it mostly up and down here, mostly coming from the up and down direction, right? It would have been kind of diagonal to the original bedding planes. And so when this rock broke, it tended to break along the foliations. And you can see the compositional layering foliations right there along this rock all over, while the bedding planes themselves are still also preserved. So you can see that they're very, very separate things. All right, so that's kind of our introduction. And so I will see you in the next lecture as we delve more deeply into metamorphic rocks.